Dear colleagues, welcome back to the School for Young Scientists. And it's our 4th day. So we had very fruitful 3 days, Monday, Tuesday, and Wednesday, with brilliant lectures, good questions, and very interesting discussion afterwards. So we're really impressed by the level of lecturers. And we still have 2 days to run. So today we have 3 speakers: Professor Yi Zheng from SUSTEC in where, help me, in Zhengzhou, no.
Shenzhen, yes.
Yes, Professor Florian Pappenbergen from Reading in UK, and Professor Jeffrey McDonald from Canada, Saskatchewan. So we are very happy to have these lecturers with us today. So Professor Yi Zheng, who will start with his lecture, received his PhD degree in environmental science and management from University of California in Santa Barbara. And he joined the School of Environmental Science and Engineering at University School of Environment, at SUSTEC, which is Southern University of Science and Technology, in 2016. He is currently the Associate Dean of the School of Environmental Science and Engineering. He is Associate Editor of a number of journals. He received several prizes for the Best Paper Awards, and he is very active in the area of water resources and related fields. So Professor Yi Zheng, floor is yours. 45 minutes lecture and 15 minutes for questions.
Okay, so thank you very much, Dimitri, for inviting me and give us a nice introduction. So I will also introduce myself and where I came from in my presentation. So I would like to share my screen with you now. Dimitri, so can you see the screen?
Yes, it's all working well.
Okay, so hello. So it's my great pleasure to give this lecture online to young scientists from Russia and probably from other countries as well. Although I do wish I could give it in Moscow. I'm Yi Zheng from Southern University of Science and Technology in China. And today I'm going to talk about hydrological modeling in the era of big data, process-based versus state-driven models. So here is a lecture outline. I will start with an introduction to the topic and then discuss the topic from 3 different aspects using research cases from my own group. So first is process-based, dealing with human inferences. Second, data-driven, coping with big data. And the third, new paradigm, physics-aware data-driven models. I will briefly conclude my lecture at the end. Okay, so several slides about me and where I come from. So this slide pretty much Dimitri has already tell you the basic information about me. So I would like to emphasize that my recent research area include hydrological modeling, watershed management, and environmental big data and artificial intelligence. So before I came to SUSTEC, I worked at Peking University, where I got my bachelor and master degree from as an associate professor at College of Engineering. So where is my university? So Dimitri visited my university, but he cannot remember. So I'll tell you, so my university, SUSTEC, is located in Shenzhen, which is a mega city in South China and adjacent to Hong Kong here. Shenzhen is often referred to as China's Silicon Valley because many Chinese high-tech companies are headquartered in Shenzhen, including Huawei. You may know that this company, I mean, the US President Donald Trump is so much hate this company, okay? So Huawei, its headquarters is in Shenzhen. Shenzhen has been the #1 Chinese mainland city in GDP per capita since 2007, and it has already exceeded Hong Kong in total GDP. Well, it's a very young city. So like 40 years ago, it was just a small fishing village. And the growth of Shenzhen is really an economic miracle. And in China, when people say something developed really fast, we would say it has a Shenzhen speed. So as you can see, after 40 years, Shenzhen has already got many titles. About my university, just like the city, it's very young, and it's only 10 years old. But the university has developed very fast. And for example, and it has already showed up in many world rankings. For example, according to Times Higher Education, our university ranks the first in the world amongst young universities created from scratch. Well, the next slide about my university. So just show you some nice pictures. So tell you that we have a very beautiful campus, and everyone is welcome to visit us at Shenzhen. Of course, not likely this year, but hopefully next year or later. Now let's move to the topic. So hydrological models, there are numerous hydrological models, and there are many different ways for model classification. I would like to use this grayscale to indicate the degree to which hydrological processes are explicitly described in the model. As you can see, at the black end of the scale are the purely data-driven models with zero process description. But at the white end are physically based model which follow physics rigorously. The wide spectrum between these two ends include some models like semi-distributed model, like SWAT, VIC, or conceptual model. Sometimes we call lumped model. The classical example is Stanford watershed model. Okay. These three types of models, are more or less process models. But in my lecture, I will more focus on the white end model, physically based model, when I talk about process-based model. Okay. So let's look at the white end. Like half century ago, Fries and Harland wrote a very classic paper which provides a blueprint for physically based hydrological model. Some basic features include the continuity between groundwater flow and unsaturated flow, coupling with surface water, emphasis on the role of vegetation, and the consideration of the influence of meteorological phenomena. So this blueprint is really influential. And since then, developing physically based model has been the mainstream in hydrology. Although someone would argue that the underlying physics is not rigorous enough yet. Some well-known model examples following the blueprint include Mike Shi, which is a very successful commercial model developed by DHI. Another example would be, I would say, Pavlo CLM, which is mostly used for academic research. So at the other end, purely data-driven hydrological modeling using machine learning has been practiced for at least 2 decades. Among all sorts of techniques, artificial neural network is the most popular machine learning technique for hydrological modeling. And rainfall runoff modeling has the most applications in this field. But purely data-driven models have not been treated as important as physically based models until very recently. when big data and artificial intelligence bloom. So, deep learning has recently emerged in hydrological modeling because it has been so successful in many different areas in recent years. So, as we can see from this figure, so deep learning is actually a part of machine learning, and which represents the hotspot in artificial intelligence. In hydrology, for example, long short-term memory LSTM networks has exhibited unprecedented accuracy for runoff prediction in ungauged basins. So LSTM is a very common deep learning architecture. Here, I just gave you an example. It's a paper published last year about the performance of LSTM networks in rainfall runoff modeling, published in Water Resource Research. So, hydrological modeling is now facing many challenges, which are also research opportunities. In this lecture, I will talk about 3 of them. First, for physically based modeling, the greatest challenge will be to accurately account for rapidly increasing human influences, such as agricultural development, urbanization, flood control, hydropower development, ecological conservation, etc. In a paper I co-authored recently, we argued that the next generation hydrological models should represent the co-evolution of the human-water nexus, which can be called watershed system models. Challenge 2. As we know that we have all sorts of sensors from ground level to the space level. They are collecting a huge volume of data about the Earth. A significant portion of such big Earth data can be potentially used for hydrological modeling, such as the remote sensing based data from NASA's water cycle missions. So then we really need a new framework for data-driven model under this big data condition. Besides these traditional or classic data, we also have new ways to collect data. So there's a concept of data crowdsourcing. Data crowdsourcing means obtaining or repurposing data from either a range of public sensor or public involvement. Okay, there's the review paper about crowdsourcing methods for data collection in geophysics, published in Reviews of Geophysics. So it tells us that a wealth of somewhat inaccurate crowdsourced information is better than merely to use a couple of more accurate data. We know that traditional sensing techniques are accurate, but because they have very high costs, so the data is of low spatial temporal resolutions. But with public involvement, like we use cell phone to collect data, or use public sensors like surveillance cameras, we can crowdsource data, and some of the data could be used for hydrological modeling. Here, I would like to give you an example showing you that data crowdsourcing for hydrological prediction is not only a concept. So my group did an interesting test. We used an ordinary surveillance camera to tape rainfall events on campus and use computer vision techniques to identify rain streaks. You can see these red lines. in this video. These are identified rain streaks. So then, with the rain streaks identified, the instantaneous rainfall intensity can then be estimated via geometrical optics and photographic analysis. So this curve shows you the interpreted instantaneous rainfall intensity. Okay, so remember that we were using an ordinary surveillance camera, not a professional camera. So the camera is very cheap. So these study results were published in Water Resource Research and also highlighted by EOS. Okay? So anyway, the main idea here is that data-driven hydrological modeling needs to cope with the huge data volume possibly being collected and coping with the diversified data types, like this kind of crowdsourced data. Okay. Challenge 3. So the competition between physically based and data-driven model has long been discussed, and the collaboration between these two model types remains a challenge. So last year, Nature published a prospective paper titled Deep Learning and Process Understanding for Data-Driven Earth System Science. This paper discussed several potential ways for the two model types to collaborate in the context of Earth system science. However, how to achieve a seamless integration of AI and physical knowledge remains an open question. In another word, can we have a hydrology-aware AI? That's a challenge to address. Now let's move to specific research cases. First is about process-based, dealing with human influences. So I will use the Heihe River Basin case to discuss this challenge. Okay, so so here I will particularly talk about the physically based model. Okay, not semi-distributed model or not conceptual hydrological model. Okay, so Heihe River Basin is very interesting river basin. It's the second largest inland river basin in China, with a total area of about 130,000 square kilometers. It has a steep, as you can see from this figure, a steep ecological gradient, which is very typical in northwestern China. So its upper part is in the Chilean mountain with snow and glaciers. Its middle part is in Heihe corridor with intensive irrigated agriculture. Its lower part is the Gobi Desert. As you can see, it has vulnerable and sparse vegetation there. Okay. Okay. Along the main stream, there are two dividing points I may refer to later. The first is Yingluoxia, which is between the upper and the lower, upper and the middle reaches, and the Zhengyixia is the dividing point between the middle and the lower reaches of the main stream. Okay, and the river eventually ends at a very beautiful desert lake called East Jian Lake. So it's a very typical setting in northwestern China. So what is the water problem? So from 1970s to 2000, excessive river flow diversion for irrigation in the middle HRB had caused the vegetation integration in the lower HRB and the drying of the terminal lake, as you can see from this picture taken by myself and these remote sensing images. Then, in 2000, a restriction on water diversion was enforced to increase the flow towards the downstream area by the central government. So it really worked, as you can see from this interpolated lake area. So from year 2005 the river is almost recovered. The lake has already was already recovered, and the lake area was kept stable at the level of 5 square kilometers. Okay, and these pictures were taken by myself in year 2016. So very beautiful for tourists. Okay? But the groundwater pumping in the middle HRB has been enhanced ever since, because the farmer found there's no enough surface water for diversion. Then they start to increase their pumping. Okay? So overall, this basin has a very typical and interesting human water nexus of arid inland area around the world. So in the past 6 to 7 years, my group has been developing a watershed system model called HEIFLOW, using Heihe River Basin as a test bed. Technical detail about this integral model can be found in a number of publications. I'd like to mention several major features of this model. So first, it has coupled diversified vegetation models. Second, it can take dynamic land use data as a model inputs. Because the land use changing is fast. When we do a long-term hydrological modeling, it's not appropriate to just use a static input of land use. Then our model has this functionality to take dynamic land use data. And the third one is it has water management modules to emulate water resources utilization activities through a complex delivery system, and emulate the impact of management policies. So my lecture will focus on this new feature. Okay, so we built the HEIFLOW model for HRB for the entire middle and the lower parts, plus a part of Basin Desert. So the entire modeling domain is about 100,000 square kilometers. So we used a grid of 1 kilometer by 1 kilometer grid for both the surface and the subsurface domains. And in the following slides, I will talk about the water management modules in HEIFLOW and focus on Zhangye Basin in the middle Heihe River Basin, because the irrigated agriculture is concentrated in this area. Okay, and the agriculture consumes a large volume of water. So what did we do? So first, we developed a water resource allocation model to emulate a high resolution irrigation activities and represent watershed management policies in integrated eco-hydrological model. Okay? So in brief, this module can internally simulate the environmental flow regulation activities. Okay, that is the diversion control by the local agency. Okay? Because the flow management activity of the local water agency are largely unknown, because the decision is adapted and not recorded on a daily basis. That's why we need a module to reproduce the decision process. Okay? So this figure shows you the regulation curve, which specifies the minimum required. This is the minimum, the y-axis represents the minimum required flow at the Zhenyi this point. Okay? This is required by the government, given specific flow conditions from the upper watershed. Okay? And this figure shows the algorithm we proposed to emulate the management decision. So here I would like to skip the technical details about how we emulate the dynamic decision process. Okay? The other thing is that the module also considers a groundwater drawdown constraint. That is, no more pumping is allowed if predefined decline limits in water table is reached. Okay, that represents the local management on the groundwater resources. Okay? So with this module, okay, we all know that modeling agricultural impact hydrological processes remains a challenge because high resolution data on irrigation activities is often insufficient. Now with this new module, so we can just start with some very basic statistics like annual statistics. The new module can internally simulate daily diversion and pumping data at the grid scale. This figure shows you the simulated diversion in blue and the simulated groundwater pumping in red at the daily time step. And this figure just tell you that the annual statistics are well reproduced. The x-axis represents the statistics, and the y-axis represents the simulated annual surface water diversion. So as you can see from this figure, the annual statistics are well reproduced by our module. And in this figure, the color actually indicates the simulated stopped pumping ratio. That is how frequent the pumping would be stopped due to the drawdown constraint. So at the grid scale, so that just show you the module can provide you very detailed information, spatial information about the water resources management activities. Okay, so we can see that this module is really valuable for water resources management. Next, we further develop an agent-based module to simulate agricultural water use influenced by water policy portfolio and coupled it with HEIFLOW. So the agent-based model considers a water management agent and farmers as water use agent. The ABM is tightly coupled with HEIFLOW at the daily time scale with two-way feedback between the agents and the hydrological processes, as shown in this figure. Okay? So we have two types of agents in play. So the water management agent has a policy portfolio for management. For surface water management, we consider the surface water resources fee as a policy parameter. For groundwater management, with the policy parameter including groundwater resource fee, water table decline limit, and the penalty rate for overexploitation. Okay. The water use agents, make their decisions based on a set of rules. And I will skip the details. And their decisions are based on hydrological conditions, crop water demand, and also the policy portfolio for water management. Okay. So let me show you some results produced by this HEIFLOW ABM integrated model. So this figure demonstrates the nonlinear impacts of water policies on hydrological processes at the basin scale. The x-axis indicates the magnitude of a policy implementation, and the y-axis indicates the responses of key hydrological variables. So these two figures shows you the heterogeneous response to water policies. In the upper one, it tells you the different lines represents different irrigation districts. So we can see that the response of depth to groundwater table vary across different districts. Okay? The lower figure illustrates the spatial distribution of a maximum change in depth to water table under the policy portfolio. Okay. So these results show that the integrated HEIFLOW ABM model is a very powerful tool to evaluate a variety of water management policies. Okay, so next I would like to talk about the second aspect, data-driven, coping with big data. So in this lecture, I would like to focus on a particular question: how to drive runoff simulation with big data. In the typical small data scenario, the model predictors like rainfall and temperature have data at a very limited number of locations only, like meteorology stations. But now, assuming we have big data for model predictor, such as remote sensing-based data fields, how to bring them into a data-driven model? There are some traditional ways we can follow. For example, we can average over the average the data field over the entire watershed. But in this case, the spatial information is not exploited at all. We can also average the data over individual databases. But in this case, spatial information is not fully exploited. You may say, okay, let's use data information at every spatial unit. But unfortunately, in that case, you will encounter a curse of dimensionality. Okay? So then we proposed a new modeling framework to address this problem. The key idea is to use computer vision techniques to transform one or more data layers into a one-dimensional feature vector as the new model predictor. So we tested the modeling framework in the upper Heihe River Basin. So we tried to predict the stream flow at the watershed outlet in Luoxian. Okay. So we extracted the two image features, intensity and texture, from different dynamic data fields. In this modeling case, include precipitation, temperature, leaf air index. Okay, so we extract the image features and eventually merge them into an one-dimensional feature vector. And this new feature vector was used as the new model predictor. So we compared this computer vision-based approach against the two traditional approaches to processing input data fields, the lump model and the semi-distributed model. So I won't go through all detail, but just let you know that if we use a semi-distributed model, we need a very heavy task on data processing and manipulation of the data. If we consider the lumped model, it's very easy to process data, but we lost all the spatial information. But with the computer vision-based approach, our approach, the image can be very easy to process, just like videos. And the new feature, the new vector can be fed into the machine learning model and drive the data, drive the hydrological model. Okay. Okay, this slide tells you how the model works. So as you can see, these dynamic data fields were extracted for features, intensity and texture, and these features were merged into 1D featured vector and fed into an ANN model, then produce the prediction. So as you can see from this slide, the model prediction well matches the observation. Okay? We test the short-term forecasting performance of our model. So we compare against the traditional data-driven models, the CV, the LM, and the SD. So I won't go through the detail in this figure, but the main idea is we have achieved a more stable performance with increase in prediction length. So the leading time means the prediction length, like a 4-day ahead prediction, 3-day ahead prediction. So our new model, the red lines, the solid line means with the preceding flow as a predictor, and the dashed line means without the preceding flow as a predictor. So in this case, we can see that our model provides a very more robust prediction results and better than the true traditional model. We also compare our model against existing process-based models for the same watershed. For example, some SWOT models in this and the web models here. So in brief, so we can see that our computer vision model is very easy to build, because if we want to build a process-based model, we really need expertise and a lot of time to manipulate the data. But it's very easy to build a data-driven model. It's much easier to build, but we have already achieved comparable or even better when we compare the Nash coefficient, even better performance for the flow forecasting. Okay, we also test the transfer learning capability for ungauged basins of the CV model. So we can see this is our method. This is a traditional LAMP model. So we can visually see that the CV model outperforms the traditional model in transfer learning. Okay. So in summary, for this part, in the era of big data, causality is no longer the prerequisite for hydrological modeling, and the correlativity is more critical. Any variable could be a predictor, such as the leaf air index in the upper HRB case. Okay, because traditional LAI is in model output, but in our data-driven case, under the context of big data, we can use LAI as the model input, as a predictor. So second, some fundamental data such as DEM may not be needed by hydrological modeling as long as its impact is reflected in the big data. So this figure shows you the matching score, it's like the similarity or the correlation between the different predictor and DEM in different time of the year. So as you can see, because the matching score is very high for temperature in the DEM. So in our data-driven model, we don't use DEM because the information of DEM has already been reflected implicitly by the temperature data field. Okay? So the proposed computer vision approach represents a very flexible way to fuse in multi-source big data in data-driven hydrological model. Okay? So the third aspect, new paradigm, physics-aware data-driven models. So now it has been more and more accepted that the physics and AI should collaborate. But the problem is how? There are two potential strategies. The first, we may introduce the physical constraints into the loss function in deep learning as a penalty term. So it's a very classic approach. Because in deep learning, we need to solve some optimization problem to get to train the model. So we can add the physically constraints into the penalty function. And a more innovative strategy is to wrap analytical solution of physical representations in deep learning as neural network layers. So here is an example about employing the unique global solution to the advection diffusion equations. It's a very innovative way. However, the problem is either strategy needs a closed form equations. But in our geoscience, the physical principles are more often represented by differential equations that cannot be analytically resolved to achieve a closed form solution. Okay, that's a challenge. So to address this challenge, we design a special recurrent neural network architecture, RNTech architecture, to encode geosystem dynamics like a hydrological model. And we call this type of neural network layer PRNN layer. Okay, this is a typical structure of RNN layer, and actually it has some algebra functions. So there are some weights and bias in these functions. Okay, so according to our new strategy, okay, The idea is that a dynamic geosystem is often characterized by the state of space representation, and are modeled by a combination of ODEs for the state variable, and also output functions for the output variable. So we can make an analogy to the RN. So we can actually replace the RN structure with some physically meaningful functions here. So we will replace the original algebra function with these physically meaningful functions in the set. Okay. Then with this strategy, we actually build in the physical model into the deep learning architecture. Okay. So this is the idea in the this is the basic idea. So this is the general architecture. So that's the traditional way for deep learning. And then we add a layer, PRN layer here. Okay. So then building in the physical knowledge. Then we also design a parameterizing pipeline. So which you can do, which takes regional dependent attributes as the input. And this parameterization pipeline provides parameterization estimation about for this layer and for the neural network layers. The technical, because of time limitation, if you are interested, you can read this paper for technical details. Okay. So I just want to show you. Okay. We build so for hydrological model, actually we build the two bucket conceptual hydrological models, wrapped it as a PNN layer into the deep learning architecture, and create a hydrology-aware deep learning model. Okay. And we use CAMELS dataset, which consists of the air average daily meteorological time series and the catchment attributes for more than 600 catchmen across the corners with limited human disturbance. This dataset is frequently used for testing deep learning approach. And we test our model against three other models. One is a partial model with only the data-driven part, and this one, and a partial model with the physically part only, and the popular LSTM model. Okay, so as we can see from the color, our model performed the best, and there are more statistics telling you that our model performed better than three other models. I will skip all the details. This is interesting. I need to spend some time. Okay, so this column shows the performance of our hybrid model, and these two columns shows the neural network only model and the physical part only model. So as we can see from these figures, so this figure means when at least one partial model works well, at least one. The hybrid model works well, very well in most cases. Okay. And more interestingly, so that means the predictive power of the partial models can be inherited by the hybrid model. Okay. So more interestingly, when we look at this non-figure, it tells you when these two parts, the physical part and the data-driven part, both do not work, neither of them work well. But we still have a large chance to have the hybrid model working very well. So it tells us that two heads are better than one. It's very interesting. Okay, we also test the transfer learning for prediction in ungauged basins. So I will skip all the experiment design, but just show you this figure. It tells you that we compare our model against the LST model. So we can see they are comparable. They have comparable performance in transfer learning, but we have more robust because we have less bad predictions. So we have much less bad predictions than LSTM model. Okay, so the implication is that because we have the parameterization pipeline, so it's very important for the PUB. And the hybrid DL model has a more robust performance than SDT. Okay? So can AI deduce? So we only use the flow data to train the regional hybrid DL model, but the model will predict snow depths. As you can see, this is the prediction. And this is the data get from NASA. And we compare the data prediction and observation. We can see they match pretty well. That's on the lumped result. We also check the different watershed. They all show very good matches. So it tells us the AI has already mastered hydrology because it never learned the snow data, but it can tell you the right story about the snow depth. Okay. So finally, I have 1 minute to wrap up my lecture. Okay. Conclusion. So first, physically based hydrological models need to incorporate human activities as internal processes and simulate a complex human-water nexus. Second, innovative frameworks are imperatively needed to take advantage of big Earth data with diversified data structures in data-driven hydrological models. We also learned from the research cases that developing hydrology-aware AI models really represents a thrilling direction for the next generation of hydrologists. Okay? So eventually, I would bring up a new blueprint for discussion. So the hydrological modeling may start with big Earth data, and we may use deep learning to process data and fuse different structures and different sources of big data. And then the data after processing, the processed data can be fed into a hybrid physics DL model to do hydrological forecasting. And based on the forecasting, we can do AI-based decision making. And of course, for making this decision, we may also need big Earth data. Here are some co-authored papers related to this lecture. And with that, I would like to stop here and thank you for listening and any questions.
Professor Zheng Yi, thank you very much for this extremely interesting lecture where you covered different things and precisely on time, which is exceptional for this school.
I was rushing.
Thank you very much.
I was running.
No, it was really great. And you also posed a number of questions that I'm sure listeners would be looking at later. For information for the audience and for you, we will, of course, these lectures are already uploaded, PPTs, I mean, PowerPoint presentations, but also we will have a video link made available after some processing because we need some processing. So it will come in several days on our website. Okay, but now it's time for questions.
Yes.
So, let me start. Okay, on YouTube there is a chat box where people from different countries put their questions and greetings and thanks to the lecturers, and one of them comes to you, of course, right now. Let's look at the questions. So first question is from Dr. Moredo from the Institute for Water Problems in Moscow. Professor Zheng, your ANN model data is very interesting. Is it a way for dimensionality reduction of input features? Perhaps Dr. Moredo means this visual, the big data component. So is it a way for dimensionality reduction of input features? Is it sensitive for blanks or errors in feature fields?
Yeah, I mean, in nature, you can view that computer vision approach as a dimension reduction approach. Yes, it's true. You can view that in that way. It's correct. And it's a good question whether it is sensitive to data area. We didn't test that, but we use the real rainfall data, which include the areas. So we were not using synthetic data. So yeah, the short answer is we didn't test that, but because we are using real data, that's so I think because after we process data, we use an artificial neural network, which is a black box model to do the forecasting. I think if there's some data area, it can be handled by the AI model itself. So it's not about our computer vision processing. It's about how effective the AI model can take care of the data error.
Right. Thank you very much. Still, of course, question remains. If you have erroneous data, it's always a problem. And if it's done blindly, sort of through automatic procedure, you may miss important blanks or important gaps. And if expert is involved, then perhaps certain things could be done to restore data, to infill the missing components and such like. Anyway, this requires further research. Thank you very much for your answer. Next question is from Professor Gelfand. How are you dealing with noisy data when coupling physically based and data-driven models? The former, the physically based models, are highly nonlinear models, so data errors may be amplified, resulting in very high output errors.
Yeah, I think this is a very good question. So because I assume so we are talking about the third part of my presentations about the hydrology-aware model. So yes, in that case, we really recommend deep learning model. Okay, if your data allow, we recommend deep learning model. So that means you have many layers. So I think deep learning, because it's because the complex structure. So deep learning has a much better performance than traditional shallow learning network to handle the error. If your data are big enough, because let's think about the error. There must be some reason for the error, right? The problem is just we don't know what caused the error. But if we have big data and we have deep learning, so we don't have to tell explicitly where the error from, but the deep learning model can implicitly handle the error. I mean, assume the data is big enough, and you use deep learning, so the error could be taken care of by the deep learning itself. Okay.
Thank you.
Thank you very much. We move to the next question. This question comes from Vladimir Matskovsky from Russia. In case of physically based neural network layer, are there special approaches for backpropagation?
Oh, you mean solving the? Yeah, I think it's solved by BP approach with some modification, because that's why we can use deep learning, because essentially it's the deep learning is like we need to solve the thousands or 10,000s of parameters within the deep learning model. So yeah, but we use the existing tools to solve that. We didn't develop a new BP algorithm to solve those weights.
I think the question is posed because instead of traditional architecture in RNN network in each node, you have different set of equations. So of course, algorithm should take care of this.
You mean the physical part?
I think this question is about the physical part, yes.
Oh, the physical part. So yes, so we still treat the physical part. I mean, like a hydrology model, a hydrological model has physically meaningful parameters, right? So, but in this hybrid architecture, we treat these physically meaningful parameters just like those neural network weights. So these hydrological model parameters are resolved simultaneously with those neural network parameters. So the BP algorithm for solve both physically based, physically meaningful parameter and neural network parameters at the same time. So there's no additional algorithm to address that part. So,
right.
So the entire architecture is just solved by the BP.
So you use the same algorithm, so simply set of parameters is different.
We don't need a separate algorithm to solve the physically meaningful parameters.
Yeah.
Okay, they were solved at the same time with those neural network parameters. Yeah.
Exactly. Thank you very much. Now, Leonid Gonchukov from Russia, Far East, not far from China actually, is asking, does that hybrid approach give the similar results to statistical or artificial intelligence post-processing of physically based model results? So idea is to use a physically based model plus error corrector based on neural network, for example, if I understand correctly.
Can you repeat it again?
So a question is about comparing the hybrid approach you have shown to another hybrid approach, which would use a physically based model, and then the results of this physically based model would be corrected or post-processed by a statistical error corrector or neural network error corrector.
Yeah. Absolutely, that's another way to combine these two type of model, and it has already been shown that it's very useful. But our strategy has unique features because with because we are using an tightly coupling approach. With that, so we can deduce, right? Like the last slide I showed, with that model we can deduce, that the AI model can deduce, because we have already built in the physical laws into the deep learning model. So when the entire model is trained, so it can deduce, even without trained without snow data, it can predict the snow depths. So that's the mismatching. So I will refer to that approach as a mismatch, like error correction or mismatch data error correction, like use AI to correct the mismatch between model and physical model and data or attention model. But that approach cannot give you the deduction capability. That's one unique feature. And the other, with our tightly coupling strategy, actually the AI can be viewed as a parameterization tool, because when the entire model trained, the parameters of the hydrological model are also inferred. So I would say that that's just two different types of collaboration between two model types, and each have a different functionality. Like our model have more than predicting the runoff. We can do many other things. Okay. But of course, that approach is also very useful. Yeah.
All right. Thank you very much. Next question comes from Nigeria, from Jeremiah Alika. Please, could you tell us what is the best approach to take when modeling sediment dynamics of any catchment? I'm not sure it refers to your lecture.
Okay. I would say it really depends on what kind of data you have. Okay. It's the starting point of model choosing. So if you have very limited number of data, so no way to do data-driven modeling for sediment. But if you have very good flow data, you may consider the hydrology-aware hybrid model. As you can see, we can train the model with flow data if you have enough flow data. And we can build in a physical relationship between flow and sediment. Then hopefully the hybrid model will also give you good predictions about the sediment if the physical relationship makes sense. Okay.
Right.
Yeah.
So what you're saying is that your hybrid approach can be also used. But I would like also to refer Jeremy Alika to some papers where indeed neural networks and support vector machines were used to predict sedimentation. If you search Bhattacharya and Solomatin on Google, you will find our paper in 2006 and a couple of other papers of quite a number of authors, and quite many people from Iran were doing this. So this work has been done, but it would be indeed interesting to use your hybrid approach as well.
Yeah, I will try. It's bringing me a good idea.
Right. Okay, we'll move to the next question. It is from Yekaterina Sharapova from Russian Federation. And this is a nice question, I think. And it reads as this: can using purely data-driven models be a sustainable solution for hydrological modeling, given climate change and human impact growth in the catchment or other water systems? Will then PRNN layer introduction do the job?
Okay, I think, of course, data-driven model depends on whether it can predict the future, depends on whether the future condition happened before, okay? So if not, then we'll say it cannot predict the changing future if the future condition never happened in your data set, in your historical data set. But that's exactly what the physics-aware hybrid model can do, right? If we have some physical rule that tells you how things would change, given some driving force, then we can use the hybrid model to predict the future condition under the climate change. That's like with the help of physical knowledges. So that's my short answer. With the help of physical knowledges, data-driven model can do that. But the purely data-driven model really depends on on your data, historical data. It's long enough or it's representative enough. Okay. Yeah.
Okay.
And about the human impact, the same thing. So if the human influence happened in the future, that will happen in the future also happened in the historical period, then it has a chance to do the right prediction. If your data, you have enough historical data. So.
Okay, Professor Zheng Yi, thank you very much. We exhausted our time given for questions and answers. Really very interesting lecture, opening new opportunities when we hybridize. So it's maybe a keyword of the last maybe decade, hybridization and committee models and hybridization of different approaches into one model, or having several models doing different things and then aggregating things. And also it contributes to the discussion which has been taking place recently. What is better, to still run our old hydrological models, or since they didn't change much during the last 50 years, to switch to data-driven? So all interested are welcome to find paper of Gay Nearing and co-authors, Karzer, for example, and answer of Professor Bavin to this. So that's an interesting discussion with taking place now.
We'll see.
Yes, and it's maybe new era of when, again, a new interest to data-driven models, but on a new level. So it's a bit of history made a circle, or rather a spiral at a higher level. When we have deep learning architectures would reignite discussion of how useful data-driven models are, as we had these discussions 20 years ago.
I think yes. Too optimistic view. I think so.
Yeah, Professor Gelfand thinks it's too optimistic to think that data-driven would solve anything. Okay, but on this positive note, we have to stop. Professor Zheng Yi, thank you very much again for your wonderful presentation. Yes,
Okay,
thank you
so
for doing
I
this.
I can quit right now.
No, just second, I want to say that you're welcome also to attend other lectures using the same Zoom
Oh,
link.
yeah, of course.
Yeah.
But
And
I just closed my video.
yes,
Okay, I will participate in the following
yeah,
lecture.
if you want, yes. And with
Okay,
this, I
thank
would,
you very much.
yes, we have now a 10-minute break and we resume at 16:15 sharp.
Okay.
Moscow time. This is 15:15 Central European Summer Time with the lecture from Professor Florian Pappenberger. So see you in 10 minutes.